Okay, this is Edmund Stark at the MSU Midland STEM Center at St. Andrews, and I am going to be talking tonight on our amazing moon. And uh, we have a slightly different look today. We're going to have some American Sign Language interpreters coming along because we may have some folks who would want that. And so you'll see an extra window, I believe. And we have a pretty full agenda. Like I said, the moon is more complicated than you expect. So I think I'm going to get started. But I'll start with a plug. Our next astronomy date is December 8th of 2020. It's another Tuesday. And so you can try to get that in your calendar if it's not already there. So tonight's agenda, I'm going to be very brief with quote homework from last month. As usual, talk about what's out in the sky tonight. We're going to talk about the main focus, which is the moon and its motions, calendars, and orbits and eclipses. And there will be a brief astronomy technology highlight. I can't ignore what just happened yesterday and this morning with SpaceX and the International Space Station. So the homework from October looked like this. And this is a collage of the various things I asked people to look at. You will receive a similar fun homework assignment because I always want to get people to get out and look in the sky instead of just hanging out and hearing what science has to offer. So this week's homework will look similar to this. It'll have a few new items and a few items that have gone away. Like, for example, we're not looking at the teapot anymore because it will have set. But I want to start out with the bright planet orbits, which, as I often do, the sun is in the middle and Earth is that green ball. We'll start out with Venus, the bright, beautiful Venus. It is inside or an inside orbit to us. And it's about over here as it's just, oh, I got to get forgot to get my laser pointer. So Venus is about here, which means it has passed its greatest elongation, its greatest distance from the sun, and it's receding from us. It's getting a little dimmer, but it's still the brightest thing in the sky other than the sun and the moon. Don't have an orbit for Mercury, so I'll draw one in on this chart. And Mercury is actually lined up with Venus and the sun right now. We don't see that, but we do see the two of them in the morning sky. Mars is down here. It has just passed a beautiful opposition, the best in the next 15 years. Jupiter is way out here, and so is Saturn. Both of them just passed eastern quadrature, this right angle line, and they are quite lined up. As you can see, if you pass a line through them from the Earth, they look very close to one another in the sky, and we will see that in the next slide. So Jupiter and Saturn together in the southwest. Jupiter is the brightest star in the evening sky. Look to the south or southwest. If you see one star, that's it. Saturn is to the left and above, and they'll be out all month. But in a few days, the Crescent Moon, remember I said it was a new moon a few days ago? So the Crescent Moon will go slowly past Saturn and Jupiter on the 18th and the 19th. And that'll be a fun thing to do. That will make it easy to see, even if you have light polluted skies, you can see how the moon moves from one day to another using these stars or these planets, sorry, as a landmark. And if you have a clear night and you pay attention, you might actually be able to watch the moon move over the course of an hour or two. Both of these planets are approaching one another rapidly. They will be closest on December 21st. And don't miss that. I will talk about that more next month. Now, Mars dominates the southeastern sky. Mars will not be this close until September of 2035. This last month in October, it actually outshone Jupiter. And right now, don't miss the Mars's special showing. If you haven't seen that beautiful, brilliant red object, almost as bright as Jupiter, take a look, because again, it's going to be slowly fading over the next year. And similar to Jupiter and Saturn, on November 24th, 25th, Mars will be passed by the moon, and it'll also give you a similar chance, maybe even a better one, because it'll be fairly close to the moon on the 25th for you to watch the moon move hour by hour. Now, in the mornings, we have Venus and Mercury. Venus, whenever it's in the sky, it dominates, the brightest thing in the sky. You can't miss it. It's not as bright as it was a few months ago, but it's still 4 times brighter than Jupiter. Mercury will be below Venus. There's a first magnitude star, meaning a quite bright star called Spica, which will be below Venus, and Mercury will be further below and a little bit to the left of that. Now, the Mercury has already passed by its peak of brightness, and it is moving closer to the sun again. So you only have about a week or so. It should be visible barely through Thanksgiving, but if you can look tomorrow morning or the next morning, it would be a good thing to do. Now, you notice I mentioned Mars, Jupiter, and Saturn in the evening. They're all visible in, let's say, by 7 o'clock, they should easily be visible. And so you can watch them, go to bed at 7:30 and get up early, maybe 6 o'clock or so, and be in time to see all 5 planets in the same night. You'll be able to get up and see Venus and Mercury. Why did that happen twice? So here's a little video I put together where the sun right now, or when this video started, was in Capricorn. And I want you to focus on Jupiter and Saturn. This is Jupiter. This star is Saturn. And over here is Mars. And this will show you their motion starting from about February or March of this year. And you will watch you will watch Jupiter and Saturn slowly move together. You can see Mars is just moving and off it goes. But now they're spreading apart again as the months go by. You can see the moon going by once a month. And then they're going to come very close together and actually pass by. Jupiter will pass by Saturn. That's what's going to happen on the 21st. And they're going to be closer than any time they have been in the last 400 years. It's going to be a very special time. So the night sky. Here's a nice star chart. This is what the sky looks like on November evenings looking south. And if you draw a line, it looks like a curve here, but in the sky, if you draw a straight line between Mars and the Jupiter and Saturn pair, below that line, as I mentioned last time, one of my favorites, a star very far south called Fomalhaut. And it's easy to see because it's a first magnitude star, very bright. And it's far in the south, and you can only see it around this time of year. But what's maybe more useful to us is this constellation here, Pegasus. In particular, this asterism, an asterism is a pattern. This is the Great Square of Pegasus. 4 bright second magnitude stars. I don't know, maybe Shaat here might be a 3rd magnitude, but these are 4 bright stars. And this actually, unlike most constellations, does look like a horse. What you have here is the body of the horse. The horse is upside down. Here is the long neck and the head of Pegasus. Here are the 2 forelegs, and the constellation of Andromeda form its 2 hind legs. You can clearly see a horse here. And this is a fun constellation and an easy one to see, at least for the square. That square will help you find the circlet of Pisces, and it will help you find Uranus, which is over here right now. I wouldn't worry about any of that. Just find the Great Square of Pegasus. And we had the summer triangle. Well, now it's fall, so the summer triangle is no longer in the center of the sky. In fact, only 1 star is visible in this map. So what we do is we simply go over here, grab west, and swing the chart around. So now we can see the summer triangle, Vega, the 3 stars, Vega, Deneb, and Altair from 3 different constellations. You remember that Vega here has this beautiful little parallelogram, which is the constellation of Lyra inside the triangle, and of course, Cygnus inside the triangle. Now, Altair will not last too much longer. It will be gone by the end of fall, but Deneb and Vega last into the winter, even though they are part of the summer triangle. And from here, the Great Square of Pegasus will be actually high over your head and behind you. You have to turn around to see it. And one more thing for the night sky, a meteor shower. The Leonids, they peak this morning, as in a few hours, 10 hours ago, but they should still be fine tomorrow morning or the day after, as long as, and by morning, I mean, let's say 3 in the morning or after midnight. That's a good time to see meteors. Maybe 10 or 15 per hour. So, pay attention to that. You're not going to see 5 every second. You're going to see 1 every 5 minutes or so. That's a decent meteor shower. And since the moon is new, it will not be glaring up the sky and interfering. So you'll be able to see even the fainter ones. Now, I have one more thing that I want you to look at, but I'm going to save that for the end of the presentation. Tonight's focus is on the moon. And before I get started on that, I'm going to stop for a moment and I'll ask my colleague, Nick, if he has any questions that have come in.
Yeah, we do have a couple questions from the audience. First one is, would you rather move to Mars or Callisto?
Well, since I can't survive on either planet, I definitely would rather move to Callisto. The joy would be seeing Jupiter, a ball about this big, rising up over my horizon, and being able to see the bands with my unaided eye. I think that'd be pretty hard. That'd be pretty hard to beat.
All right, and the second question that we have so far is, what is Spica? I've never heard of it.
Okay, Spica is a bright first magnitude star, and it is in the constellation of Virgo. And Virgo is one of the zodiacal constellations. It's actually a fairly large one. It takes the sun a reasonable amount of time to get through Virgo. So it's one of the brighter stars in the sky, and it's definitely one of the brightest stars in the zodiac. There's Castor and Pollux, which are bright stars, and Spica and Regulus, which was in Leo, which I just showed you. Those are pretty good. Those are pretty good constellations. They're pretty good stars.
Okay, a few more questions are starting to pour in. How do constellations get names?
That is a good question, and it has no single answer. Many constellations are fairly obvious in the sky, such as Pegasus, the horse, or the winged horse. Leo, the lion, looks like a lion. Scorpio looks like a scorpion. They have been known for thousands of years, cultures going back to Greek and even Babylonian or Assyrian. Some of the other constellations were named quite recently. Many of them were named by Hevelius or some people who are in the 16 and 1700s when the first detailed star charts were put together, detailed by modern definitions. Most of them were named, let's say, by Ptolemy's age. So by 150 years after Christ, you would recognize the star charts.
Okay. Next question is, how old is the moon?
Well, the moon is roughly as old as the Earth. So I don't know the exact date. We're looking at 4.5 billion years to decide at what point you start the clock. Under 5 billion years is my understanding of what science is claiming.
Okay, this person asks, will the Leonid meteors be visible between 3A to 5A? I'm guessing they mean 3 to 5 a.m.
Yes, that might even be peak time. The Leonid meteors typically aren't visible before midnight simply because Leo is not in the sky. So you'll see a couple shooting out from up above the horizon. And that can actually, if you have a good shower, that can actually be kind of fun to watch because the showers tend to rise, the meteors tend to go up as opposed to going down. It's a little different. But yeah, the normal time is in the early hours of the morning. So that would be just fine.
Okay. How big is the Ursa Major?
Big in the sky. It's one of the largest constellations we have. because Ursa Major, for those of you who are not familiar with it, the Big Dipper is the tail of the bear, and the four stars in the pot are half of the body. But it continues on forward to a nose, and it has three large legs and paws. So it's a fairly big one. Um, in terms of, I don't know if like a solid geometry angle will help you, but it's like 15 degrees across one way to the other, and maybe a little bit larger than that. And so that it's pretty impressive.
Okay. We the number of questions keeps growing. Why
Uh-oh.
do all the planets not have air?
Um, maybe a better question would be, why do some have air and some don't? Um, I'm sorry about this one. I'm going to have to pun. Pretty much each planet has its own reason for having an atmosphere or not. But one thing I can say is that the larger the planet is, the more likely it is able gravitationally to hold on to whatever gases it came with. The further it gets from the sun, the easier it is for those gases to remain because they don't get so hot. But you get far enough away from the sun, and those gases can tend to condense into liquids or solids. And then, let's say, while you have a lot of methane, it's a liquid or a solid, and then you don't have gases again. So every planet has its own problem there.
Okay, this person is asking why were they named? I'm not sure if they're referring to stars or constellations.
Um, I'm going to guess it's constellations, and they were named because some of them actually look like them. Others, people, I guess you just need a little bit more imagination, um, because some constellations don't look like anything, and yet they have a name.
Okay, and here's a relatively quick one. Where is Ursa Major on a chart, and are Ursa Major and Ursa Minor bear constellations?
They're both bear constellations. Ursa Minor is right by the North Pole. In fact, the tail is the pole star Polaris, if that means anything. Ursa Major is always in the north. Um, I'm not sure right now which way it's pointing. I think it should be kind of standing on its tail, on its handle at this point, but it is always encircling somewhere in the north. So sometimes the dipper points up, sometimes the dipper points down, and sometimes it's sideways. It depends on the time of the year. I didn't show it because my charts, I always show looking south because that shows the planets crossing the sky. If I look north, I wouldn't see the planets. And I also show it south because that's what changes every year. If I showed the skies to the north, you would see more or less the same constellation circling around. So to me, the interesting part is in the south.
Here's a fun one. How old are the stars?
Um, that depends on the star. We know of some fairly new stars that have been hatched that are only a few 100 million years old, and some that I'm sure that are much younger than that. And we definitely see old stars that are many, many billions of years old. The nearby ones in our galaxy that we identify as stars. Um, there are stars older than that in other galaxies further out, where all the stars are that old. And globular clusters also have stars of like age. So those are fun to see. But stars' age varies tremendously, going back to beyond 10 billion years for some of the oldest and the smallest, which is how that works out.
So, how many more of these questions would you like to answer before we move on?
We should probably, if there's any that have more to do with what I just described rather than general astronomy questions, I would like to tackle any of those, and then we should move on.
I, uh, I guess, what are shooting stars? They aren't really stars, but they know that they aren't shooting stars shooting across the sky. But what are they?
So shooting stars are the meteors that I just described. Can I go back? We're over here. Yeah, so these are shooting stars. And they come from a small grain of sand or dust called a meteoroid, which comes from space and hits the Earth's atmosphere at tremendous speeds and burns up and creates a flash of hot air, air heated so hot that glows. And that streak of air, glowing, burning air, so to speak, is what we see as a meteor.
Okay, and I guess one last question for now. When is the next time the Leonids will produce a storm?
I don't know. They produce storms every now and then. I don't have my meteor showers memorized. I think the Leonids are a 33-year cycle, but it might be the 17-year. I don't remember, but it's not this year. And if they do produce a storm, it will be fairly brief, and it'll only be like one night for a few hours. So you pretty much have to be looking for it. But if they do produce one, you'll hear about it here, assuming I'm still doing these. Are we good?
Yeah, I'd say you're good for now.
All right. So the moon, I'm going to talk about the phases of the moon, the daily motion of the moon, its appearance, its orbital motion. I'm going to spend some time talking about the full and the crescent moon. A lot of stuff to talk about. So what does the moon do in the sky? Very simple question. It moves, of course, left to right in the sky, just like everything else. This is due to the rotation of the Earth. The sun rises in the east, gets high in the sky, and sets in the west. Every star does the same. All the planets, they all do the same thing. Never in the north. Remember, I just was talking about that. Ursa Major plays in this area. That's why my maps usually go to the south, because that's where I think where the fun part is. But the moon does more than move. It has phases, and that's due to the moon's orbit around the sun, or sorry, around the Earth. Now here, if you look at this inner chart, you notice that the moon, no matter where it is always half lit, just like the Earth is half lit, just like any planet is half lit. When we look at, let's say, last quarter moon, we're looking right down this line and we see one half the moon lit and one half not. But when we're looking over here at a crescent, imagine looking at this part of the moon here. This is mostly the dark part, and we see mostly dark and mostly light, but the moon is still half lit. We're only seeing part of it. Now, the phases start from new moon, which is when the Earth is at one end of the moon and the sun is at the other, and they form a line. And the crescent slowly grows. Waxing means growing, so it's a waxing crescent. First quarter. Then during all this time is the gibbous phase between first quarter and full moon. Then we have a waning gibbous. Waning means getting smaller. Last quarter, waning crescent, and new moon again. That's a full cycle. Now, these points where the moon looks half lit, you might want to call that half moon, but they're called first and last quarter because they are the first quarter away around the full cycle. Full moon is half. This is the third quarter and new moon. You can tell time using lunar phases. Using this diagram, imagine that the sun is shining over here and lighting this part of the moon. If the moon is full, then it is on the opposite side of the Earth from the sun, which means if the sun is setting, the moon is rising in the east on the other side of the sky. When the full moon is due south, that means the sun is as deep as it's going to go below the horizon. It is midnight. When the full moon is in the southwest, halfway to setting, it must be 3 in the morning, about halfway to 6. If the full moon hasn't gotten south yet, it's 11 o'clock. You can play the same game with the first quarter moon. We know that at first quarter, the moon, the Earth, moon, and sun are at right angles. So when the sun is setting, first quarter is at a peak, high point in the sky due south. If the first quarter is setting, you know it's about midnight, and so on. And you can use the other phases to tell time as well with a little bit more practice. Now, how long is a month? Where does that fit in here? Where does the word month come from? Well, think moonth, okay? 1 month is one lunar cycle from new moon to new moon or first quarter to first quarter, whatever. It's called a lunation. The Islamic calendar starts out with clerics seeing the hilal, the crescent moon. You can measure the length of a month yourself. I prefer going from first quarter to first quarter, but you pick a phase, record the date and time, and wait till it gets to be that phase again, and record it for a couple hundred, 100 days, just looking at when that phase appears, and then average. And you will get about 29 and a half days. This is an easy project for school. So if a month is a month, why do our months have 31 days instead of 29 sometimes? Well, the problem is not with the moon, it's with the sun. Because 1 year, the Earth goes around the sun, it takes 365 and a quarter days. 12 of these lunar cycles, new moon to new moon, takes 354 and a third days. So we are 11 days off. How do we solve that problem? That is something that various cultures have done in different ways. And I'm going to talk about some of those. One way is you add a short intercalary month. That means in between the calendar after you get 12 months. So in Egypt, ancient Egypt calendar, you have 12 months of 30 days, and then you add an extra 5 epigomenal days. Isn't that a good word? You don't get to use that often. 5 epigomenal days, and you get 365 days for the year. And they also had a leap year system. Another way of doing it, which is the old Roman and the current Chinese lunar calendar, is you add a normal intercalary month every 2 or 3 years. This is a really good solution because that way every month is starting from new moon to new moon. All the months are correct. And every 2 or 3 years, you just toss in another month in order to get the calendar to stay with the sun. One option is ignore the moon. People have seen the Aztec calendar, and why isn't it coming? There it comes. So this is what this is a line drawing of an Aztec calendar. They had no period correlating to a lunar cycle. They had 18, what I'm calling months, but they were 20 days long. And then they added 5 nameless unlucky days to round out the year. Another option, ignore the sun. This is what the Islamic calendar does. There are 12 months. Each of them is either 29 or 30 days, depending on when someone sees the crescent. And it is 354 days long. And therefore, it's 11 days off from the year, and that's tough luck. It cycles around. So a given month in the Islamic calendar can either be spring or winter or fall. And if you live to be 30, 40 years old, you will see all of these in your lifetime. Of course, then there's a solution you're familiar with. Add days somewhat randomly to each of the 12 months so that you have 12 months with various days and they turn out to be 365. That's what we've chosen to do. The calendar is a topic I'm probably going to talk about on a future astronomy night because the calendar is a completely astronomical thing. And it's a lot of fun. But speaking of calendars, one last point about lunar cycles, full moon names. You've probably seen these. We talk about the harvest moon or the hunter's moon or the long night moon. These are actually from the native Algonquin peoples learned by New England colonists. The different Algonquin tribes had different names. All of them had the June moon as the strawberry moons. Apparently strawberries were important to Algonquins. But one more name I'm going to talk about is the blue moon. This is an extra full moon in the season, usually the third one. But in 1946, there was someone in Sky and Telescope who slipped up and mentioned that it was the second full moon in a month. This definition has stuck. So now if somebody asks you what does a blue moon really mean, almost everybody will give you this definition, which is about a little less than 75 years old, a little more than 75 years old, fairly recent. And let's talk about blue moons. Here is a table that shows all of the blue moons in America in the world for the next 20 years. In 2018, we had 2 blue moons in a single year. We had 2 moons in January and 2 moons in March. That pattern is repeated in 2037, so it's a pretty unusual thing. And another special full moon recently was the total lunar eclipse of January 21st of last year. So That's something that tends to happen on a full moon. We'll talk about that later. But when we're looking at the full moon, what do we actually see? Turns out we can see a lot. Visible to the unaided eye, this region here in the south is the lunar highlands. It's a very bright region. And much of the rest of the moon has lots of dark spots. These are called oceans and seas. The ocean of storms is the most obvious, but everything that you see named, all of these named seas are visible without a telescope if you have decent vision. And you can even see several craters. Most people can see this huge crater of Tycho, maybe not the crater itself, but these ray systems dominate the southern part of the sky. Copernicus, a huge ray system in a dark part of the sky, is visible. And some people can see Kepler, another large crater. But there are also things in the moon which hard to say whether you want to say they're really there or not. Um, Pareidolia, another fun word. Seeing patterns like shapes in the clouds, ink blots. How about the man in the moon? What does that mean? So this, you see a lot of drawings like this. I have never seen much in the crescent moon, but what about the full moon? Do we see anything there? I'm going to show you a few things. This, when I drew this because I wanted to see when I see the man in the moon, this is what I see. I see the sea of, I think this is the Sea of Tranquility, as in Tranquility Base. And here, part of the Ocean of Storms. And this huge thing here, a mouth with kind of teeth, that's what I see when I'm actually looking at the moon. The other thing I see is the lunar bunny, two long ears, a nice fluffy tail. This, I think, this is more obvious to me than the man in the moon. But I've seen other people who have claimed to see this. I find these two harder to resolve. They look like one big blob in my eyes, but hey, I'm getting older. But here's one I don't see much, but I've seen lately because I just noticed it. Smiling polar bear with dark glasses and a shiny black nose. Can you see the polar bear in the moon? Here's the shiny nose, the big dark glasses, and the smile. I'll let you decide. And if you can go on the internet, I actually pulled this. I know you're not supposed to take stuff off of Wikipedia, but they had a whole bunch of stuff here on Wikimedia. They have a different bunny. This is one that's pretty good. Once you see this woman, the hairstyle and the smile, you'll be able to see her. But she's a little harder because the details are finer than just the big old clumsy man in the moon that I see, or the bunny. So I've talked a little bit about the motion and the phases, the appearance, especially the full moon. I'm going to stop here for a moment to ask if there are any questions that are like related to this. If you have questions, you can ask them as they come up. But I'm going to ask Nick Henton, my colleague, to hold off general astronomy questions until the end, and then we'll work on answering those.
Okay, focusing on moon-related questions. Where does the word moon come from?
I don't know. Boom. It's just like I don't really know where the word sun comes from. I mean, it has origins in other languages, but at some point people had to come up with names for things. So you got me on that one. I don't know offhand.
Okay, let's see here. There are quite a few questions to sift through. How big is the moon?
Um, Two answers to that. One answer is the moon's about I think it's like 2,200 miles across, 2,200 miles in diameter. So it's fairly large. It's a little bit larger. Maybe it's 2,300. It's a little bit larger than 1/4 the size of the Earth. And I've got a slide showing that coming up. Another answer, how big does it look in the sky? Only half a degree. And I'll show you how small that is later on in the talk.
Okay. Why does the moon glow?
The moon glows because it doesn't glow of its own light like the sun. It shines like all the other planets by reflecting light from the sun to us. So sunlight reflecting off the moon is why it shines. with one exception, which I'll also talk about in this talk.
Okay. How does the moon affect the tides?
I will talk about that later too. I'll just
Okay.
the last thing in this talk is basically the tides.
Excellent. Okay. What is the most detailed part of the observable moon?
Well, by telescope, the more powerful your telescope and the better the conditions, the more you can see. But I think the place where there's most detail visible to the naked eye is where these two craters, Tycho and Copernicus, are, because you're seeing an actual individual crater. And over here by the Sea of Crises, and this area here has got lots of spots. So Sea of Crises and the Sea of Serenity, and the oh, what is this one? Of showers. I can't remember its Latin name. Um, and so this area, I think you see a lot of detail.
Okay. And does everyone in the world see the same phase of moon?
Pretty much, pretty much. The moon is roughly 250,000 miles away, usually just a little bit less. And from one side of the Earth to the other is about 8,000. So there is a little bit of a difference in perspective, but it's not too much. What it will do is it'll affect the timing of eclipses, but not whether you see an eclipse or not.
So here's a question about one of the fun vocabulary words you used.
Mhm.
What does epigomenal mean?
Um, as far as I know, I've only seen that word used for additional days thrown into a calendar that are not part of a normal month, but it more or less means extra.
Okay. How does the moon spin around the Earth?
Well, the moon spins on its axis like the Earth does, causing days, and the moon revolves around the Earth due to the Earth's gravity, and that happens roughly once a month. And we'll be talking about how that works. That might be our very next topic. Actually, after brightness, I think I'll be talking about that.
Okay. Why are there blue moons?
It's just called that. I think that there may have been an early meaning of a blue moon when there's like a little bit of haze and the moon actually looks a little blue. I've seen that personally, but uh, for some reason they call that a blue moon. That there's if you have a second moon in 1 month, remember if a month is supposed to be a lunar cycle, there can only be one full moon in a month. But since we have 12 months and that extra 11 days, eventually a second full moon is going to sneak into a given month.
Okay. And I guess I have a question directed at you, Dr. Stark. How many more of these questions do you want to answer before we move on again?
I would tend to err in moving on rather than answering questions. You can always answer questions at the end.
Okay.
But
I think
I want to focus if there's any questions where somebody might not understand what we've been talking about, I'm happy to deal with those. But I don't want because I don't want to keep people here too much later than 8 o'clock because it seems like we're going to be later than 8 o'clock.
okay, I guess just one last question then. Why are they called seas?
Well, that's a good question. Um, they are called seas because when you look at the moon, you see these dark areas. Um, they reminded people of seas. So let's say that when people looked at the moon with telescopes for the first time and they saw I'm not going to talk about that tonight. They saw mountains and they saw craters, but then they saw broad areas that didn't seem to have any features in them. They thought those were seas. They literally thought they were water.
And with that, I think I'll let you move on.
All right. So the upper parts here is what I'm going to be talking about next. In particular, one obvious change that you'll notice is brightness. Sometimes the full moon can be absolutely overwhelming. You can read a book by moonlight, um, but it's surprising how much it actually varies. The full moon, we see the entire lit face of the moon. When it's a quarter moon, we see half of it. You might expect that the quarter moon is half as bright as the full moon. But if you know how to read magnitudes, the full moon is up here at 0 degrees and quarter moon is at 90 degrees. It turns out that the full moon is not twice as bright, but 12 times brighter than the quarter moon and over 100 times brighter than the crescent. So the brightness of the moon varies wildly. And so I want to talk a little bit about that to give you a sense of that. Here's a, if you go from 100% reflecting all light to 0% reflecting no light, you know that ice and snow and bright clouds, high clouds reflect 60, 70, 80% of the light. Water, dirt, tree leaves absorb a lot of light. On average, the Earth is about here at 0.31, what I'm going to call a bond albedo. We'll just talk reflectivity. The moon is down here at 0.12, barely a third the brightness of the Earth in terms of reflecting sunlight. So wouldn't it be neat if we could compare them both under the same lighting conditions? Well, we have spacecraft. We can do that. Here is NASA's or NOAA's Discover satellite, and it used its EPIC camera, Earth polychromic imaging camera. This, by the way, this orbits the sun. It's looking at the solar wind. So it's far from the Earth. So it can look back and see both the sun and the moon. And this is an image it took. It optimized the exposure so that the Earth looked normal. This thing that looks like a rusted out old quarter is the moon under the same lighting conditions. And this isn't a composite image. This is the moon actually passing in front of the Earth from the spacecraft's point of view. And this is how dark and dingy the moon is when it has the same light. That's where that point, that 12% reflectivity comes in. But nonetheless, it's bright enough. Many people have not noticed this. The moon is easily bright enough to be seen in broad daylight. I have a lot of pictures like this. Isn't one of my pictures, but a lot of backpacking pictures like this up in the mountains. The contrast is lower because the daytime sky is so much brighter, but still the moon is perfectly flaming obvious, especially in gibbous phase. At crescent, it's a little harder to see because it's dimmer and it's closer to the sun. So crescent is harder to see, but it's still there. Another obvious change that you would see when you start observing the moon is its height above the horizon. Sometimes when you're looking at its peak height, which is again always in the south, it rises, gets high, and then sets. Okay, we talked about that. Sometimes it's almost overhead, it seems. Other times it's barely just a few degrees above the horizon, about 20 degrees or so. This does not correlate with the lunar phase. In other words, a full moon can be really high or low. A crescent moon can be really high or low. But it does correlate with the seasons. That's kind of interesting. And that's also a hint because the season have to deal with the Earth's tilt and its motion around the sun. So there must be a connection there. That's a good hint for us to follow. Imagine that the Earth is spinning on its axis and the sky is a big glass ball around the Earth, and the Earth is spinning in the center. This ball is tilted. You'll see globes are always tilted by some angle, 23.4 degrees. Tilted relative to what? To this. It is tilted relative to where the Earth goes around the sun in that big circle, or from our perspective, where the sun goes around us. That's what it looks like, because it looks like the sun is moving on this glass sphere. All right. So this is called the ecliptic. And this is a projection of our equator onto the night sky. And this is that 23-degree angle right there. So the moon and the planets all travel in this line, more or less. So this is a very interesting part of the sky. And you remember from school, you probably learned latitude and longitude. Here's the equator of the Earth and the latitude lines going east and west, and the meridian lines running north and south. Well, we can take those lines and give every spot on Earth a coordinate. Here are the coordinates for Midland, Michigan, right there at the junction of the rivers. Well, we can do the same thing. We can project those things onto the sky. Here's the equator, and here is the ecliptic. The longitude lines are called right ascension. I don't know why. That's just what they're called. And the interesting thing is, they're not measured in degrees like they are in the Earth. They're measured in hours. It takes the Earth 24 hours to rotate. So each one of these lines is 1 hour long. And that's helpful for astronomers. If two stars are 2 hours apart in right ascension, we know that when one star passes a certain point, 2 hours later, the second star will pass it. So it kind of makes sense. And here's what that looks like on a star map. I've chosen Orion here for one reason, because most people recognize the belt and the shoulders and all that. But a better reason, look at the equator at 0 degrees. The equator in the sky passes right through the top of Orion's belt. Mintaka is the name of that star. The ecliptic, which is this line where the sun and the planets travel, go above the whole top of Orion. So the entire constellation lies below the ecliptic. And if we plot out the whole sky, this doesn't have like far north and far south, but the main part of the sky, we see the ecliptic rising high. Here's Orion, you recognize it again. High above Orion, and then it comes back to the equator, and then it goes low in the area of Scorpio and Sagittarius. It's very low there. So since the moon travels here, when the moon is in Sagittarius and Scorpius, it's low in the sky, 22 degrees below, 23 degrees below. And here it's 23 degrees higher than the equator. And that happens seasonally. In the winter, the sun is low. The full moon will be very high in the sky. In summer, when the sun is high in the sky, the full moon will be very low in the sky. Other phases behave differently, and you can probably figure that out for yourself. I'll just skip over some conversation I was going to have about that. So the location of the moon depends on the season and on the time. So for example, in September, the sun is near the autumnal equinox, which is this spot right here. The sun will be in here. Okay. So if the moon is just past third quarter, which would place it here, if it's just past third quarter, it would be over here, and it would be a thick crescent. It would be in Gemini, and it'll be high in the sky. Okay. And so you can play that game for any phase or any time you want, any season you want. So let's look at some crescent moons. Okay, here's a beautiful crescent. The lit side always points towards the sun, which means the sun must be over here someplace, therefore a little down, which means it's below the horizon. Since the sun rises and sets, it always goes from left to right. So the sun, if it's down here to the right, has already set. So therefore, this is a waxing crescent just coming up after sunrise. Here, the crescent points this way, so the sun is down here. Since the sun always moves in this direction, it hasn't risen yet. This crescent, therefore, is a very old waning crescent before sunrise. Now we have this thing here. What's with that? Let's talk about that a little bit. The sun moves along the ecliptic, and so does the moon. What happens when this ecliptic strikes the horizon? Let's look at some of those star charts from past sessions. Here is the chart in September pointed towards the southwest or the west where the sun sets. Here's the ecliptic forming a gradual angle. This is where the sun and the planets travel. So if the sun is set here, there's a crescent over here, it will be fairly low in the sky and angled to the right, pointing at the sun. In March, however, the sunset will be different because the ecliptic is nearly vertical looking towards the west. So the sun will be down here, the crescent will be high in the sky, and it will look like a smile because it will be pointed down towards the sun. And the opposite of true is true for sunrises in March. We could spend a lot of time talking about this. I just want to give you a flavor for that. So let's look at these crescents again. This waxing crescent after sunset is a September crescent. This waning crescent is an April late crescent before sunrise. And this one is also a waning crescent, but it's in September. Notice how the September waxing crescent and the waning crescents are dramatically different. But I made some major assumptions. Everything I'm telling you is for you to use. Those of us who live in the United States, in the north temperate latitudes, and in Europe for that matter. For people living near the equator, the crescent moon is always a smile. For people living near the North Pole or the South Pole, the crescent, when you see it, is always facing sideways. And of course, the southern hemisphere is different and mostly backwards to this. But there's one more feature of the crescent moon. It's called earthshine. I mentioned that the moon shines from reflected light from the sun. Look at this picture. Here's where the lit part is, but you can clearly see features of the moon here. This is not lit by direct sunlight. That's the crescent part. This part is lit by light reflected off the earth and hitting the backside, the unlit side of the moon. This is called earthshine. And the Farmer's Almanac, the almanac I took this out of refers to this as the new moon in the old moon's arms. I thought that was kind of nice. And briefly, I want to talk about the crescent moon on flags. This is very common in Islamic majority nations. And you might wonder if this has to do with the practice of sighting the crescent moon to start the month. But now that you know a little bit more about lunar phases, you know that this is a waning crescent. This is the end of the month. So this has nothing to do with the hilal. This is actually a symbol of Byzantium that was adopted by the Ottomans. So this is a good time to stop. I've talked about the full and the crescent moon, but I haven't yet talked about orbital motion. So are there any good moon-based questions?
Yes. Why does the ecliptic move?
Well, the ecliptic doesn't really move. If I can, it's probably easier to just go back up here. But when we look at this image here, where our equator is like this, but since our Earth is tilted, the ecliptic goes around like this, and sometimes it's high and sometimes it's low. And it's because the Earth is tilted with respect to its orbit. So the ecliptic is not moving in itself, but it's just a line that goes at an angle around the sky, and the planets and the sun move on it.
Okay. Here's a question not specifically about the moon, but I feel still important to define. What does celestial mean?
Ooh, very good. Celestial is of the sky and of the stars. Because what was in the sky and what was in the stars was considered to be perfect, unlike the imperfect life we have here on Earth. This view persisted for 1,000 years or more. Very often, beautiful music or anything of great beauty or purity is often called celestial for that reason. But celestial basically means of the sky. So that's why we talk about a celestial coordinate system, to make it different from our Earth-based coordinate system of latitude and longitude.
Okay. When are we able to see the craters and the seas on the moon the best?
The best time to see anything on the moon is when it's near the light and dark line, which is called the terminator. If you want to see the craters on the moon that have the big rays like Copernicus and Tycho that I've talked about, full moon is fine. And if you want to see all the seas, full moon is fine. But the moon is, even though I talked about it being gray and dark, there's so much light shining on it that it can be fairly bright, and it almost gives you, I don't want to say moon blindness, but it may take a while for you to look at it and get your eyes adjusted, because the whole sky is black and this one spot is brilliant. And until your eyes become adjusted, it can become a little difficult to see the difference in seas, etc. But you can see those easily with binoculars, more easily with binoculars. But you can see all those things with your naked eye. All the ones, at least, that were highlighted in that image. There are many more. There's like bays and marshes, as they called them. They all named them after water. But the big picture things like tranquility and serenity and fecundity, all those things you can easily see.
Okay. What does declination mean?
So declination here, since it's on this figure, is the equivalent of latitude. So when we talk about the Earth, if this was the Earth, these would be lines of latitude, these parallels of latitude. In the sky, they're called declination. I can guess why that is because it lines, decline from the equator back and forth, but I don't know why that name was chosen and not latitude.
When did earthshine start reflecting on the moon? Is it related to us using power and lights? And is this what causes the reflection?
Oh, that's a good question. No, absolutely not. The Earth is a very highly reflective planet, especially when it's cloudy. It gets lots of light shining off of it. And so it is sunlight. As much as we use lights and all this stuff, the light that we put out is a much smaller quantity than what the sun dumps on Earth and reflects off.
Okay, and this person is asking, wouldn't earthshine light up the same side of the moon that always faces us and not the dark side of the moon, as your slide said?
Okay. This is something that maybe I might want to spend a little time on. The dark side, I don't know if I have a slide that will show this clearly. Um, but the dark, I'll have to go back a little bit. There's two concepts here, okay? The moon is rotating as it goes around. So there is a side that always faces us. That's why we always see the same face. I'll talk about this later, but that is different from the dark side. Right now, when we see the side that's facing us, when it is not lit, it is the dark side. The side that faces away from us is the far side of the moon. That side we never see, except for the very end of the talk. I'll talk a little bit about liberation, but we never see the back side of the moon. But the dark side, we see that half the time. Right now, anytime there's a waning crescent, the dark side of the moon is the part simply that's not lit, and sometimes it's looking right at us.
Okay, and let's see here. I think maybe just one more question for now. What does vernal equinox mean?
Ooh, yeah, that's a fancy term. So vernal equinox, where am I here? I can do this. Here's the very next slide anyway. Um, in the summer, when the sun is up here, we have long days and long nights. In the winter, the sun is down here. We have short days and long nights. Long days and short nights. I don't know if I said that right here. And in these two spots where the sun crosses the ecliptic, we have equal day and equal night. Equinox means equal night. So the night equal to day. So this is in autumn, and this is in spring, which is called the vernal equinox or the spring equinox. So this point here at 0 hours right ascension is the spring equinox. That's all that it's all that vernal means is the spring equinox. We use the same word sometimes when we talk about vernal pools, those puddles in spring that dry up by summer and live long enough for fairy shrimp and things like that. So I believe you said that was the last one we would take for now.
Yeah, I'd say in the interest of time.
Yeah. So here we have orbital motion, rotation, and some of the effects on the Earth. So the moon moves 360 degrees in a circle. It takes a month to do this. It comes out to about 13 degrees per day. How much? Oh, let me get back into, sorry, slideshow mode. So how much is that? Let's go back to Orion. We'll zoom in a little bit. So let's put the moon over here. There it is, just a little bit above the ecliptic there. The moon moves over the top of the horizon. Look how small the moon is. I've actually made it a little bit bigger than it really is, but against the stars, this is about how big the moon would look in terms of the constellation. And in one day, it would move about that far. Okay. And in 29, or sorry, so in about a month, it's going to come back. Now, this might give somebody an idea. Instead of trying to guess when it's first quarter and then trying to guess when it's first quarter next month, why don't we use the stars to measure? If we can like pick a time when the moon is right close to this star, we can nail the time of that moon period down to the nearest half an hour, and we can really use the stars to lock in the moon's position and measure the month much more precisely. So suppose we do that. We'll choose a convenient star to mark. Let's choose this one. And then we start watching, and the moon slowly goes away over the course of a month. And by the time it comes back to here, we measure that time, and it is 27.3 days. This is not even close to the 29 and a half days. And it's clearly the wrong phase. If we waited for it to get back to the same phase, it's all the way over here. That's our 29 and a half day number, but the moon is 30 degrees further east. So what is going on? This is something that is easy to measure. You can't miss this. 2.5 days off, 2 1/3 days off. So what's going on here is, let's look here at this angle. I try to use NASA's drawings when possible, but they often have a lot of mistakes. The sun needs to be much further up than this. But here is the line of the new moon going from the Earth through the moon towards the sun up here. And this is where it's pointed towards that star that's distant. Now, as the moon starts rotating around the Earth is moving around the sun, so that by the time the moon gets back into the same orientation, which we just measured at 27.3, the sun is now over here, and the moon has to travel a little bit of an extra time over here to get back to new moon to catch up. That's that 2 1/3 extra days. So there are two different months. The sidereal month, which is one orbit around the Earth, the time it takes the moon to return to the same position against the stars. There's the synodic month. That's from, let's say, new moon to new moon. That's the 29 and a half. But while we're really trying to measure this closely, because that was our goal, we can't help but notice that this synodic month is not 29 and a half. It definitely varies from just a little over 29 to almost 30. Some months are longer than others, and the winter months are consistently longer than the summer months. How is that happening? So there are two things that we're going to notice when we're measuring the moon against the stars. One is what I just described. The synodic month isn't constant. And the second is the moon does not follow the ecliptic like I just told you it usually does. It's usually above or below. And you can't miss this because it will be passing early on in the talk. You saw the moon passing over Mars or under Jupiter. Why is that? So that's what we're going to talk about first. So here we are. This is the star chart I showed earlier. The moon's path can be anywhere between the red lines, very far above and below the ecliptic. You can't miss this. So is that 5 degrees important? Turns out it's critical, because what's the most cool thing you can see in the sky? An eclipse. Here's a photo I took of the lunar eclipse in 2019 from my backyard. Here's a photo I took from Wyoming of the solar eclipse back in 2017. Now, you may or may not remember what causes eclipses. A lunar eclipse is when the sun, earth, and moon are in a line, and the moon is therefore in the earth's shadow. A solar eclipse is when the sun, moon, and earth are in the line, and a part of the moon's shadow falls on the earth. But now, wait a minute. This is exactly what I described as the lineup for a full moon. And this is what I described as the lineup for a new moon, when the moon is between Earth and the sun. So why don't we have a lunar eclipse every full moon and a solar eclipse every new moon? It's because of that critical 5 degrees. The moon's orbit is tilted. Here's the ecliptic where the sun goes, we'll talk it like Earth centered, the sun goes around the Earth. The moon has an angle of 5 degrees in its orbit. So when the moon and the sun line up, the moon is too low or it's too high to cause an eclipse. There's only a period of about 36 days here at each of these places where the orbits intersect. Those are called nodes. And it's only at these places you can have an eclipse. Now we can measure that too. What is the difference from between here and back to here? You'd expect that would be the 27.3 days that we saw earlier, but it's not. It's 27.2 days. That might not seem like a lot. It's only a tenth of a day, but look at it this way. Over the course of a year, you've got 12 and a third months, lunar cycles, or actually a little bit more. And that's a day and a half off every year. That's not something that is missable if you're paying attention. That is, you're gonna see that. So what's going on is that the moon is coming around, but instead of landing here, it lands here the next month, and it lands here the next month. This node is moving backwards. And because it's moving backwards, the moon doesn't have to travel as far to hit it. And so this is called the recession of the nodes because they're going backwards. And it takes 18 and a half years for it to come all the way back to its initial spot. So I talked about this first one down here, get rid of that. And we're going to talk about this next. But I now want to point out we have 3 months. The orbital time, the sidereal month, the synodic time, which is the phase, full to full, and the draconic month, the time between centers for eclipses. And astronomers have known about this since 1,000 years before Christ. That's how easy this is to measure if you have the time. So why does the synodic month vary? Why is it not constant like the other two? For that, we need to turn to the 1600s. Johannes Kepler, probably the most famous astronomer of all time. He developed his 3 laws of planetary motion, and that's what we need. Because what he discovered was that the Earth, the planets don't revolve around the sun in circles, they go around them in ellipses, which means a slightly flattened circle. But what's more important is that the sun is off center. Whoa. So that means then if the Earth is going around the sun, it seems to be moving, the sun seems to be moving more quickly here because we're closer to it. So the speed of the sun as we see it is different here versus here. Kepler's second law says when the Earth is close to the sun, it's not just an apparent change, it actually moves faster. Those two things combine. So here is a drawing of the sun. This is exaggerated with the Earth's orbit around it. Okay. So right here, this happens to be in January when we are closest to the sun. That means the movement here is faster. And as the moon goes around the Earth, it has to go further to get back to new moon so that the month is longer at that time of the year. Contrarily, down here, the Earth is moving very slowly and it's far away. So the moon catches up sooner and the month is shorter. So that variation in month is not due to sloppy measurement. It's due to the motion of the Earth around the sun. So does this bring a question? If the orbits like this are elliptical, then wouldn't the moon's orbit around the Earth be elliptical? The answer is yes, it is. Then, is there anything that we can tell about this elliptic orbit? Yes, there is. If we put the Earth here, the moon also has a close point and a far point in its orbit. And I'll show you what that is. To scale, if this is the Earth, this is what the moon looks like in the same size. But let's make the whole thing to scale. We'll make the Earth about this big, move it off to one side. Then to scale, the moon will be this big, and we'll move it off over to there. And this distance is pretty much what the Earth and Moon look like. If the Earth is this size, the Moon would be this far away. And to complete the picture, the Sun is a football field or more away, depending on the time of the year. Now, if the Moon's distance varies, does it look bigger or smaller? When things are closer to us, they look bigger, right? Well, the answer is yes. That is what we call a supermoon, which you probably hear about every now and then. To the same scale, this is what the moon looks like at perigee when it's closest to us. When it's furthest, it gets to be about this size. Here on the screen, this is an obvious difference. In the sky, you would not notice this. It's closer and much brighter, but again, your memory of the moon here versus the moon half a year ago, it's not going to happen unless you do science and measure it. Now, NASA there's some obvious ways we can measure it. Now we can measure it with a camera, okay, the size. But you can take a clipboard and measure the size of the moon, you holding the clipboard at a constant angle. And this NASA site here, this JPL NASA site, has got some procedures to that. But are there any other effects from this elliptical orbit? Let's measure the timing. We'll measure the timing from, let's say, close approach to close approach, okay? And we could do that by measuring the supermoon. What do we think? Which one of these is that going to match? None of them. 27 and a half days from close approach to the next close approach. Now what is going on? Well, it turns out that this close approach slowly moves. And it is longer than this 27.2 days. So we're before the draconic month kept getting closer and closer. Here it's getting further, so it takes longer to reach. So I'll have a picture of that here. So suppose we're over here at this furthest part. That's easy to see. When we go around and come around again, we don't come over to here, but we come to here. And since this is further, the moon has to travel a little bit further to get there. So this month is even longer. And it comes around again and it ends up being over here. This is exaggerated, but now we have 4 months. The phase month, the star month, the month of eclipses, and the month of the moon's distance. Okay, and this one takes almost 9 years to come back to its spot. Are there any other effects from the moon's elliptical orbit? Yes. Now we can talk about the rotation rate. The moon turns on its axis once per orbit. And does that mean it doesn't rotate? No, because remember, we see the same face every time. So it's turning once. This rotation rate is constant. But if the orbit is elliptical, the speed isn't constant, which means libration. The moon doesn't turn at the same rate that it revolves around. And the easiest way to do that is this little thing here that I've shown, not this big obvious spot here, that's the Sea of Crises, but this thing here called the Smith's Sea. As the moon gets older, here's a very young moon and it's just getting older. Watch what happens with the Smith's Sea. Here it's right on the horizon. And by full moon in this particular cycle, look, it's gone. Because this is libration. Here we're seeing this part of the moon that we're not seeing now. And similarly, these two craters here, this is Grimaldi and Riccioli, two Jesuit astronomers. When you look at where this thing has gone, look at the difference. We're seeing slightly different faces of the moon, just by a few degrees. You probably wouldn't see this with the naked eye, but with binoculars even, if you're paying close attention, you can see this. So the last thing is, how does the moon affect us on Earth? Some of you may remember this guy, an actor named Lon Chaney, made a number of great movies where he became a werewolf every month. Now, I'm not going to comment on the like an increase of werewolves every lunar cycle, but I will say that scientists have long studied how people behave weird during the full moon. And if you think I'm making this up, I am not. This is a object of study, or at least it was in the past. Think of these words. What's a lunatic? What is lunacy? What does it mean when you call somebody loony? These are all words from lunation and lunar, from the root word is luna, name of the moon. Um, and they describe how people behave weird during full moons. But here's a more measurable effect on the moon. This is the famous Bay of Fundy. Down here is high tide, looks normal. Up here is low tide. You can't even see the water. And these can be up to 50 feet difference, these tides. And there's 2 cycles a day, high, low, high, low. And they take every 24 hours and 50 minutes between the second high and the second high and the second high. Now that's not one day, that's 50 minutes off of a day, but what it is it is the time between high moon and high moon. That gives us a hint. It is in fact the moon which dominates the tides. And here's a picture and pulled out that the gravity, all gravity is very sensitive to distance. And the moon is relatively close to the earth. So its pull here is greater than its pull here. And it creates a bulge of water on the near side and the far side of the earth. So as an object rotates, here it is low tide. 6 hours later, it's high tide. 6 hours later, it's low tide. 6 hours later, it's high tide. And then we're back after 24 hours and 50 minutes, we're back to low tide again. So that's how we experience these things. High tide when the moon is overhead, and low tide when the moon is off to the side. But the strength of the tide literally depends on the phase of the moon, because the sun also has a gravitational tide. So when the earth, moon, and sun are in a straight line, whether here for new moon or here for full moon, both are pulling the same bulge in the same direction, and you have a high tide that's really high and a low tide that's really low. The opposite occurs during neap tide when you have the quarter moons, when the sun is pulling this way and the moon is pulling this way, and they counterbalance each other. So high and low tide are much more moderate, and those are called neap tides. And I have to correct the figure. The moon's tide is actually twice as strong as the sun's, and this has it shown the other way. And you can't find everything perfect on the internet. I take what I can get. So we're almost done. I have to talk about the astronomy highlight, the technology highlight. Today, SpaceX delivered 4 astronauts to the International Space Station. They used a Falcon 9 rocket. They used a Crew Dragon spacecraft, and they delivered 4 astronauts. This is the return of the United States to peopling the spacecraft. Even though we had lots of astronauts up there for the last 20 years, ever since the shuttle program stopped, they had all been sent on Soyuz, in other words, Russian rockets. So the rocket was launched on Sunday. It arrived docked late Monday night, and early this morning, the astronauts got on board. And this is what the International Space Station looks like. Been in orbit since November 2000. There's been continuous research ever since then. And I'm showing you this for more than the reason that it just happened today. This month happens to be a really good time to see the International Space Station. Yes, with your unaided eye. The ISS is really, really bright, and it's moving. When it is in the sky, you can't miss it. It's brighter than any plane, and it can be even brighter than Venus. And if you happen to catch it in good binoculars and you're steady, you could even see that H shape if it happens to be facing in the right direction. Now, here is a list, and I'll include this in the material if you request it. Here is a list of times when you can see the space station will be visible for 4 minutes or for 5 minutes. It appears here 18 degrees above the horizon, it goes high, and then it comes back down. And so all that data is here, and I'll be happy to send it to you. But the second half of November is a really good time to see the space station. There are a lot of good opportunities. and it moves fast. It goes around the Earth once every 93 minutes or so. So, and what's fun is that it doesn't disappear in the horizon. It disappears when it enters into the Earth's shadow. So it suddenly appears, it's there, moving really bright, and then all of a sudden, poof, in the mid sky, it's gone. It's a fun thing to see. So, um, homework, rather than just rehash this, these are all the things I asked you to look at, including catching a flyover at the International Space Station. And it's time for questions. I've put the general topics out just as a, a teaser for questions. And I'll also mention one more thing: to request a copy of the observing tips and the timelines for the ISS, you can email me at this address. And don't forget, next month, December 8th. So what do we have for questions?
Well, we have a lot. um, let's start with this one. Why do we study the moon?
Um, well, the general question could always ask, why do we study anything? But we study the moon because it is the easiest astronomical body to study. We can see all kinds of features on the moon, all the craters, all that stuff. We also wonder we can start at, we've been asking questions like, where did the moon come from? How long has it been in its current orbit? What is it made out of? Is it made of, does pieces of it come from the Earth? By analyzing the moon, do we get meteors that hit the Earth that come from the moon? Is there water on the moon? Could we establish a colony on the moon? Could we put people on the moon as a base to going onwards, let's say to Mars or other planets, where we don't have to escape Earth's tremendous gravity all the time? All kinds of reasons to study the moon, other than it's just a really cool thing to do.
Related to that, let me find the question real quick. I lost it. I'll look for it later. What was the best moon you've seen?
The best moon I've seen would probably have to be an eclipse. And so anytime you can, and what's neat about an eclipse is that even when it's in the total shadow of the Earth, you can still see features. Like you may remember I had the photograph of the total eclipse, and you can still see the seas and the ocean of storms. You can still see all those features, and it's deeper. Air can be deep red. Sometimes it's kind of orange. I've seen a few eclipses in my life, and so those are always fun.
Okay, and I found the question that I was looking for. Since water was found on the moon, what will we do with it in the future?
Well, that depends on if we go back. I mean, the current plan, I believe, is they're hoping for a return to the moon around 2024, which is not that far away, really. Um, and imagine how dreadful it would be if we had to carry our own water. Think of the size of the rockets we'd need. So if we can find a way to get water from the moon that's convenient and energy efficient, et cetera, it would literally save us a fortune, rather than having just to take water from the moon instead of having to carry it with us. So finding water on the moon, in terms of like a practical question, would primarily be for um, human, I don't want to say colonization, but at least humans being on the moon.
Yes, like human occupation, perhaps.
Yeah.
How close did the Russians get to landing a man on the moon?
Um, that's a good question. Um, I don't know the answer to that directly, but I can say this. When Apollo 8 was in the planning stages, it was planned to be a Earth orbit mission, because it was only going to be the second time people have gone on to the Saturn V. Um, but I don't know if it was the CIA or a military plane, took a picture of a monstrous Russian rocket on the launch pad. And it was very clear that this had no conceivable purpose other than a potential moon rocket. So NASA became afraid in the space race that the Russians were going to get a person around the moon sooner than we were. So they actually changed the schedule of Apollo 8 to make it a lunar flyby instead of what Apollo 9 was initially supposed to be. So that, if my timing is right, this is a long time ago. If my timing, I was a little boy. I think that was in 1968 that Apollo 8 flew, give or take a year was in 68. And so in 1968, the Russians had a rocket that they were thinking was going to go to the moon. And I also know that they did, in fact, have a lunar landing modeled out, meaning the landing craft. At what point they gave up, frankly, they may have given up their program when Apollo 8 went around the moon. So they were maybe a half a year off, perhaps, behind us in the race.
Okay. Next question. How do craters get made?
Craters get made for the most part when meteors or perhaps small asteroids or comets strike an object. There's lots of meteor craters on Earth, but because Earth has things like seas, where if it hits most of the Earth is ocean. If a meteor hits the ocean, it's not going to leave much of a crater. We have things like forests and trees. We have which overgrow things and cause erosion. We have rain, which causes erosion, and maybe most importantly, we have continental drift and subduction. So craters and cratered surfaces simply get buried underneath other plates. Moon doesn't have any of those things. You make a crater on the moon, it's there for billions of years. That's the major reason why the moon is so cratered, because the Earth has a much greater gravitational pull than the moon. It's clear that many more pieces of space junk have landed on the Earth than have landed on the moon, but our surface has been scoured over.
Here's an interesting question about getting involved in astronomy. How can the public become involved in finding near Earth objects, either by sorting data, targeting specific sections of space, by a crowdsourced home telescope search, or some other way?
Um, I think the easiest way to do that, and I don't know if it's being done, not so much a crowdsourced personal telescope thing, but it would probably be looking at images that have already been taken. This just this past summer, I led a group of 8 students who were not looking for near Earth objects. They were looking for brown dwarfs using research data that there is just more data than there are people to look at. And you can do computer simulations, but computers will miss things. And so I know that there are things like that for brown dwarfs. There are things like that for dwarf planets, um, or rogue planets. Sorry, I misspoke. I suspect there is, if you want that specifically to get involved in, I'm going to guess that there might be something where you could look at finding, you could join a group, a research group where they are actually looking through data, because that's a very important thing. We don't want asteroids to land on the Earth without any warning.
Uh, I guess one last question. It's sort of a group of questions that are all very related. Is the moon gravitating away from the Earth? Why does the moon orbit the Earth, and why doesn't it fall down and hit the Earth?
Yeah, so that's a good question. Um, Normally, things don't collide in space because there's so much space out there. The moon's orbit, as we've described, um, wobbles around. It has a long axis, but it keeps spinning around and around at different angles. The planes of the nodes recess. So it's a stable orbit, but it doesn't repeat itself very often. Um, and the Earth's gravity is pulling on the moon, just like the moon's gravity is pulling on the Earth, and they're both rotating around a common center somewhere inside the Earth. I think the Berry center for that system is in the Earth, and so um, it doesn't fall in because I guess I could use this analogy. If you took a gun and fired a shot horizontally, parallel to the Earth's surface, it would fall to the ground. If you had a bigger gun and fired a shot a little faster, it would curve down to the Earth, but it would still eventually hit the Earth. Now imagine if there was no air resistance, a lot of imagining, suppose we're on the moon, but there's no air resistance, no air, and you fire a really big cannon and the object begins to curve down, but it curves down at a rate that matches the curvature of the Earth. That object is now in orbit, and as long as there's no friction, there's no air, there's nothing slowing it down, it should remain in orbit indefinitely. So an object in motion tends to remain in motion. The Earth is constantly pulling at the moon. The moon is, if the Earth were to disappear, the moon would fly off. But since the Earth is here, the moon is traveling at such a speed that it's not fast enough to escape, but it's too fast for the Earth to pull in, and so it's beautifully balanced.
All right. Thank you for your time. I apologize if there are any questions that we haven't answered. We got a lot more than we usually get, so I had to prioritize.
That's a good thing, but maybe a bad thing. I love answering questions, but I don't want to have anyone, miss out. But you have, if you really have a question that you want answered, you have my email address here, and you can fire me an email there as well. And I will do my best to answer those questions. All right. So again, thank you for joining us. Join us again if you're interested. Next Tuesday, December 8th. Do I have a topic yet? No, but I will have one by then. And if you want a copy of the observing tips that I gave and the timetable for the space station flybys, or if you have a question you want answered, send an email to starkyd@msu.edu, and I will do my best to get back to you soon. Thank you very much. See you next month.